For today's lesson, you'll learn how to work with analog input signals and pulse width modulation on your ESP32. We'll explore some of the common built-in sensors available on your ESP32, such as the Hall effect sensor and touch sensors. We'll test the analog to digital converters of your ESP32 using a potentiometer. You'll also learn how to set up PWM channels and attach them to multiple GPIO pins of your ESP32. At the end of this lesson, you should be able to create a prototype consisting of red, green, and blue LEDs where we can adjust the light intensity through a potentiometer and can be selected through the touch sensors. Hi, my name is Joe Edgo and welcome to Lesson 2 of the IoT Development Training course with ESP32. For this experiment, you'll need the following materials: your ESP32 development board, 3 LEDs, red, green, and blue, 3 current limiting resistors. Values could range from 150 ohms to 470 ohms, a strong magnet, 10 kilo ohm potentiometer, a couple of connecting wires, breadboard, and a micro USB data cable. Let's look at our circuit diagram. We'll start by connecting our potentiometer to our breadboard. Recall that it has 3 terminals. One end will be connected to the ground, and the other end to the positive 3.3 volts of your ESP32. The middle terminal, which is the wiper, is going to be connected to one of the 18 available analog to digital converter pins of our ESP32. You can use any, but for this demonstration, I'll be using the ADC on GPIO 13. Then, the 3 LEDs, red, green, and blue, with their corresponding current limiting resistors, will be connected to GPIO 22, GPIO 19, and GPIO 18 respectively. Again, you can use any GPIO pins available that you desire. And finally, we'll attach 3 floating wires for our touch sensors. Similarly, you can use any of the 10 available capacitive touch sensor pins of your ESP32. Here, I'll be using touch 0, touch 3, and touch 5, which are connected to GPIO 4, GPIO 15, and GPIO 12 respectively. Now, let's implement our circuit connection. Place your ESP32 board on the breadboard. Make sure that you connect the 3.3 volt and the ground pins of your ESP32 board to the positive and negative bus strips of your breadboard on both sides. Now, let's write some Arduino codes to test our connection. First, we'll test the built-in Hall effect sensor on your ESP32. The sensor is located behind the metal lid of your ESP32 module. So, what is a Hall effect sensor? And what are its common use cases? Well, a Hall effect sensor is a type of magnetic sensor that can detect variations in the magnetic field in its surroundings. It can be used for detecting the strength and direction of a magnetic field produced from a permanent magnet or an electromagnet. The greater the magnetic field, the greater the sensor's output voltage. For example, the Hall effect sensor can be combined with threshold detection to act as a switch. One of the common uses of magnetic sensors is in automotive systems. It can be used to count the number of revolutions of a wheel to compute the distance and speed of a car. It is used to calculate positioning, detect proximity, detect closing of doors, and much more. Reading the Hall effect sensor measurements with the ESP32 using the Arduino IDE is simple as using the Hall read function. Let's take a look. First, let's define three constant values for the red LED pin at GPIO 22, the green LED pin at GPIO 19, and the blue LED pin at GPIO 18. By the way, the hashtag define in Arduino is used only to give a name to the constant value, like some sort of a placeholder. It does not take any memory space on the chip because it only replaces all mentions of this constant with its value at the compile time. And then, I'll declare and initialize an integer Hall data. This is where we store the value that we will be getting from the Hall effect sensor. In the setup function, I'll set the pin mode of the three LEDs as output. And let's have our serial monitor with a baud rate of 115200. Now, inside the void loop, all we need to do is use this Hall read function. Then, in the serial monitor, I'll display the value we receive from the Hall effect sensor. Now, let's upload our program. And then, let's check the values received in our serial monitor. As you can see, the value received ranges from about 40 to 50. This is without the presence of a strong magnetic field near the ESP32 module. I have here a magnet for my cell phone holder. In your case, you can try and experiment any magnet that is strong enough to be detected. Now, notice that as I place this magnet on top of this module, the value received drops significantly, reaching roughly to negative 180. Now, I'll twist it to the other side and the value received is greatly increased, reaching to positive 300 plus. Now, let's modify this program and use this Hall effect sensor value to act as a switch. And depending on the threshold that I want, I could create a condition that if the Hall data is below 30 or the Hall data is above 60, then I can say that there is a detectable presence of a magnetic field near my ESP32 module. In response, I'll turn on the three LEDs. Otherwise, I'll turn it off. Okay, I'll upload the code. And now, notice as I place the magnet near the ESP32 module, the LED starts to flicker a bit. Then, when the condition is satisfied, the LEDs turned on. In our connection, we captured both the lower and the higher threshold of below 30 and above 60 for the LEDs to turn on. And depending on the magnet you're using and your desired threshold, you can change these values accordingly. Now, let's understand how the built-in touch sensors of your ESP32 work. I'll define three values: red touch pin, T5, green touch pin, T0, and blue touch pin, T3. These correspond to touch 5, touch 0, and touch 3 of the ESP32 respectively, and are represented by the three hanging wires in our circuit, colored red, green, and blue as well. Then, I'll also declare and initialize three integer variables for red, green, and blue touch data. These variables will hold the value received from the three touch sensors. To read values from the touch sensor, simply call the touch read function and pass in the GPIO pin we want to read. And then, I'll print the value to the serial monitor. Then, I'll duplicate this code and change this to green. And last one, change this to blue. Let me adjust this code so that it's a lot easier to see on the same line. Also, I'll add a 1-second delay and re-upload the program again. As you can see, the values of our 3 touch sensors are ranging between 55 to 65. Now, see what happens if I touch this red wire. The value of the red touch data drops, ranging from about 12 to 7. The same goes with the sensor on the green wire. As well as on the blue wire. Now, let's use these red, green, and blue wires to act as a switch. So, I'll create a condition that if the red touch data is below a certain threshold, say 50, I'll turn the red LED on. Otherwise, I'll turn it off. I'll duplicate this code twice and then change all this red to green and all this red to blue. Let's upload our code. And now, observe what happens as I touch the red wire. The value reads below 50 and the red LED is turned on. The same goes with the green LED. And of course, with the blue LED. We can touch 2 wires or all wires simultaneously, and our code is able to respond accordingly, turning all the 3 LEDs simultaneously. Now, let's understand the analog to digital converter in our ESP32 using a potentiometer. I'll define another value, pot pin, at GPIO 13. This is where the wiper terminal of our potentiometer is connected to. Basically, the analog output voltage 0 to 3.3 volts of this wiper terminal will be sent to the GPIO 13, and using the analog read function, we should be getting an equivalent digital value. So I'll declare and initialize an integer variable, pot data. This is where the equivalent digital value from our analog input will be stored. Note that the ESP32 uses 12-bit resolution for its ADC. So it means that we are expecting a possible range of values from 0 to 4095. Recall that in your Arduino Uno, the ADC is only 10-bit resolution. So the value you read is only between 0 to 1023. I'll also declare another variable, voltage, of type float. Here, we'll do some simple computation to compute for the equivalent voltage being read. We are expecting to read a value between 0 volt to 3.3 volts. Next, we simply call the analog read function and pass in the GPIO pin 13 connected to our potentiometer. And similarly, let's display the ADC readings from our potentiometer to the serial monitor. Now, let's upload our code. As you can see, the initial value being read from our potentiometer is 0. Now, as I turn the knob clockwise toward the direction of the positive terminal, it gradually increases its value. And the max value is 4095. And if I turn it on the other direction, toward the ground terminal, the value drops and the minimum value is 0. Now, instead of displaying the value ranging from 0 to 4095, let's have a simple formula to compute for its equivalent voltage. So, I'll cast this integer pot data to float and then divide it by 4095, then multiplied it by 3.3 volts. And finally, I'll display the equivalent voltage of the 12-bit ADC reading to my serial monitor. So let's upload the program. If you want a full explanation on how the analog signals are converted to digital signals in Arduino Uno, please check the link in the description below. I'll open my serial monitor, and as you can see, as I rotate the knob of this potentiometer, the equivalent voltage received is being displayed. Finally, let's talk about pulse width modulation in ESP32. PWM is a way to control analog devices through digital means. So, PWM is not true analog output. PWM only imitates an analog-like signal by applying power impulses, or short bursts of regulated voltage. Note that ESP32 has two true digital to analog converters, or DACs, to control analog devices. But for this topic, we'll experiment first with the PWM. So, PWM is one of the primary means by which microcontrollers drive analog devices like variable speed motors, dimmable lights, actuators, and speakers through digital means. In ESP32, PWM must be configured first before use. The ESP32 has a LED PWM controller with 16 independent channels that can be configured to generate PWM signals with different properties. You can use any channel from 0 to 15. In my program, I'll use channel 0. Then, we need to specify the PWM signal frequency. Recall that in Arduino Uno, the PWM frequencies are 490 Hz and 980 Hz. In ESP32, we can set each PWM channel to a much higher frequency. In this example, I'll create a constant frequency and set it to 5000 Hz or 5 kHz. And finally, the resolution is also configurable. ESP32 PWM can be programmed anywhere between 1-bit to 16-bit resolution. Note that in Arduino Uno, the default PWM resolution is 8-bit. In here, let's try setting it to 12. Note that the PWM frequency and resolution are inversely proportional and is dependent on the clock source. Now, in the setup function, you need to call the LED setup function and pass in 3 arguments. The first is PWM channel, then the frequency, and the resolution. Next is the LED attached pin, and pass in the GPIO pin that will be attached to the PWM channel. Note that you can attach multiple GPIO pins to a single PWM channel for them to share the same configuration. So, I'll attach the green and the blue LED pins as well. Note that there are also other functions that you can use in the LED API. For example, you can use the LED detach pin function to detach a pin in a PWM channel. And then, finally, the last function that you need to call is the LED write. This is quite similar to the Arduino's analog write function. This requires 2 arguments, PWM channel and the duty cycle. And since our pot data variable holds a 12-bit ADC value from our potentiometer, we can simply pass it here. Our pot data has values ranging from 0 to 4095. I'll also remove this 1-second delay so that you can see the glowing and LED fading effect in real time. let's upload our code. And as you can see, the three LEDs glow in sync with the potentiometer's knob rotation. The LED's light also fade as the knob is turned toward the negative terminal. Note that you can experiment on these variables. For example, instead of 12-bit, we can use 8-bit resolution. So now, it only has 256 discrete duty cycles. It means from 0 to 255. That's 2 raised to 8. But since our pot data receives a value from our 12-bit analog to digital converter, thus, we need to map these 4096 discrete duty cycles to only 256 discrete duty cycles. So, I'll create another variable here. To be precise, I want an unsigned 16-bit integer as my duty cycle. And then, I'll use the map function to map this pot data from 0 to 4095 possible values to a new duty cycle value of 0 to 255 only. And then, I'll use this duty cycle as an argument here. Now, let's upload and test our code. And for your circuit connection and programming challenge, I want you to implement a similar circuit but using different GPIO pins. Same as with the example, the three LEDs glow and fade in sync with the potentiometer's knob rotation. Now, the three hanging wires will act as a selector to the three LEDs, wherein if the blue wire is touched, only the blue LED can be controlled. However, if the green wire is touched, only the green LED can be controlled. And the same goes with the red wire. Again, thank you very much for watching, and if you've learned something of value here, please click the like and subscribe button, and don't forget to hit that bell icon to get notifications for every new video that I uploaded for this course. See you in the next lesson.